I'm going to record this if possible, if that's rather not if possible. If that's okay with you guys, I'll record this. I'll make it available for other folks afterwards. Plus, it's probably going to go a couple of hours. My morning class went a couple hours, and it's only a few folks could stick around the 2 hours. But what I plan on doing is just going through the entire review packet and just talking through it and knocking it out. So that's what I'm going to do. Please stop me if you have questions, but otherwise I'll just go ahead and crush on through it. Figure that'd be a good way to do the review. Let's see here. Okay, let's see if I can switch cameras and get that to work. Can you even see I have my coffee here? Yes, good. All right. Let it begin. Okay, so, let me make sure I'm within the camera view. Okay, cool. All right, so rockets and controls and signals and all kinds of stuff, right? So that's what this GR is going over, and let's get into it. Okay, number one, briefly explain the relationship between atmospheric pressure and nozzle exit pressure for the following conditions. Okay, over, under, and ideal. Over, under, and through. So basically, I just cut out the screenshot from the video online, but I also kind of want to illustrate it real quick. So overexpanded is where you have my rocket nozzle, right? And the atmosphere pressure is squishing it in the middle. You would think overexpanded would be the one where it kind of has a skirt on it, but that's not true. Over is where, let's see how I want to do it. I want to say the pressure of the atmosphere is greater than the pressure on the exit velocity. So that atmosphere is kind of squishing it back into this inverse cone kind of shape. Contrast that with underexpanding. That's where, pressure of the atmosphere is not enough to actually really shape it very much. And you do get this kind of a plume, that goes out to each side like this. So that's underexpanded, weirdly enough. And then ideal, well, ideal is what we search for and what we strive for. And it's where you have like no squish and no plume, and the atmospheric pressure is just balanced with the exit velocity pressure. So that's what those really look like. Okay, 3 types of chemical rockets. Well, there are a few I can think of. Solid, liquid, hybrids. These are types of chemical rockets. There's actually a kind of rocket we call electrical rockets, which is we talk about those, magnetic fields that basically eject out, what would you call it? Ions, essentially, but that's not what we're talking about here. Chemical rockets are like a solid rocket is filled with this grain, this explosive grain, basically. And once you light it, that sucker is just going to go, which is kind of one of the downsides. It's tough to throttle that off. It's not impossible, but it's really, really tough. But they're simple. And because they're simpler, they're cheaper, they're more reliable, and they can sit on the shelf for longer. So, for example, if you have an ICBM, it's a pretty good thing. So you don't have to keep worrying about changing out the fuel over time, right? Liquid rockets, on the other hand, are also great. They have the unique ability for you to throttle them really precisely, like how much thrust do you want, how much you can, change the blend of your fuel on the fly. You can turn them on, turn them off. But they are more complex, so they have the potential to be less reliable and more expensive. Usually what we see is you have a liquid, core booster and then solid boosters strapped on, or multiple solids. You don't usually see this last kind called a hybrid, which mixes some of the elements of solid and liquid. I've not seen a whole lot of those, but they exist. So those are your three types. Okay, specific impulse. So ISP is defined as, I always call it bang for your buck, and that's pretty common. Or put another way, the efficiency of your booster. Just checking, make sure the camera can see me. Okay, good. Efficiency of your booster, of your rocket, I suppose. Like how much bang, so which is to say how much thrust are you getting for your buck, which is your unit of fuel, whatever that is, if it's a kilogram of fuel. So like higher ISPs are better. That's what we want. So high ISP is good. Now you could have lower ISPs for a particular purpose of some kind, right? You might, for example, like the first stage of a rocket is often not that efficient. You're just trying to get your rocket up in the atmosphere, and that is an inefficient process, just cradle to grave, end to end. But if you had your druthers, you'd want rockets that were more efficient. Yep. So, as a side note, we measure this in seconds, which is a really weird unit for efficiency, but that's how we do it. So that's what ISP is. Okay. I love these names that we have in the review packet. Fishy sat, fat sat, flat sat. They're all great. Let's see here. Let me make sure. Sorry, my Teams video like flips the orientation, so I have to make sure I'm good. Okay. Fishy sat, whatever, is equipped with a cold gas thruster, which has an ISP of 120 seconds. Okay. Neat. Calculate the total delta V Fishy sat can produce if it has a dry mass of 300 kilograms and can carry 50 kilograms of propellant. Aha. Okay. Let's see here. Actually, let me close my Outlook so it doesn't make. Okay, cool. G naught. So let me just kind of actually sum up here for a second. Let's go to the other side of the equation sheet. We're going to be in the propulsion area of the equation sheet. We're going to be using what we call the ideal rocket equation. Where you basically take into account the efficiency of a rocket, G naught, which is just Earth's gravity, and the mass of the whole system before you burn and the mass of the whole system after you burn. Now you might say, why do we use Earth's gravity if, what if we're going to launch from the moon or something, or Mars, like Elon Musk is talking about? Well, I don't know, but I do know, I checked with our resident astronaut, Colonel Payton, Gary Payton, and he said, yeah, it's just the way we've always defined the ideal rocket equation is to be based on Earth's gravity, and that gives us a common basis across time. That's what constants do, right? They allow us to make comparisons. So it allows us, even though it's weird, like we might launch from other planets someday, it allows us to compare the efficiency of rockets no matter where we're going to launch from. So, okay. So it says here Fishy Sat has a dry mass of 300 kilograms. So like the whole satellite itself is 300 kilograms. And then it can carry 50, it has a fuel tank. And then this is 50 kilograms of propellant. Okay. So it's asking, well, if I burned everything in my fuel tank, how much bang could I get? How much delta V, rather? So ISP, it says 120 seconds. G naught, we can plug in real quick there. And take the natural log of dry mass plus the fuel over the final mass, which is we burned through all of our fuel. So just 300. And then we plug in chug. $181.281 meters per second. So heads up, because we had meters per second squared here, seconds here, so we get meters per second out. And that's okay, but just to kind of compare it to what we've done with like HOMA transfers and stuff, where we had like, 3 kilograms or 3 kilometers per second, or, in that realm, this little cold gas thruster is barely giving us anything when we compare it to that. But you don't generally use those to do delta V's. You just use it to kind of keep your satellite pointed and stay in its little orbital location. So, all right, cool. Right. Advantages and disadvantages of staging. Okay, so advantages of staging. You can basically to put more mass into orbit. How would I put this? Relatively speaking, more mass compared to like a single stage. So it's also more efficient. And I guess kind of in the same way that you can put more mass into orbit. It's a more efficient thing. But staging, remember, is stacking multiple rockets on top of each other, essentially, or strapping rockets to each other. So disadvantages of that are it's more complex. And because of that, it can be less reliable, depending. And it adds expense, I would say, more expensive. Because you're strapping different rockets together, sometimes from different, companies even. You have to integrate them all, but ultimately, we always choose two stage. We just have to. Like usually, that's just the truth of the matter. So, coffee sip. Sorry. All right. So now let's do the math of staging. Given a two-stage rocket, so let's say here, I'll just draw this bad boy. Stage 1, stage 2, and then the satellite on top. Okay. It says calculate the total delta V the launch vehicle produces when carrying a 4,000 kilogram payload to space. Okay, I am going to put that in here. I'll put it right here. This is a big thing people forget, so don't let it be you. Don't forget that you have to incorporate the launch of the actual satellite, the mass of it, because that's what we're launching in space. Okay, so this actually ends up being real straightforward. We're going to do the ideal rocket equation once. We're going to do it again. And then we'll add them all up. Okay. So let's think about stage 1. We'll take these kind of in turn. Okay, stage 1. So again, we have ISP, G naught, natural log, M initial over M final. Okay, so I'm just looking at the stage 1 line here. So the ISP of that bad boy is 300. Ooh, nice. G naught is always 9.8. Now, here's where we make our money. M initial is the mass of everything sitting on the pad before we have lit the fuse, basically. So that's going to be the mass of the structure of stage 1, which is just the rigid metal tube, the propellant, which is what fills it, stage 2 structure, stage 2's propellant, and the satellite's mass. So basically everything. 20,000 plus 290,000 plus 3,000. I'm going to run out of space, watch. 1,000 plus 4,000. Ah, it didn't run out of space. Boom. Okay, so that's the initial mass, is everything sitting on the pad. And just kind of thinking your way through the story is really important here. Just where am I in the story? So before we launch everything, or before we light, I should say, before we light the fuse kind of stage one, that's the mass of everything. The M final of stage one is after we burn through all the propellant. So it's going to be the same math up here minus the propellant, right? We're not going to add that in. So I'll put a 0 right there. That's how I draw zeros. Sorry, it looks like a phi. Plus 0 plus 3,000 plus 21,000 plus mass of the satellite. Okay, so really the only difference between the M initial and the M final is all the propellant we burn through in stage one. Ta-da, let's plug and chug.
Wait, sir, quick question.
Yeah.
You said you include the propellant from stage 2, just not stage 1.
Yeah, you do. So, yep, exactly. So basically, M final is after we have burned through stage one's fuel, but everything else is still attached, and we haven't even cut stage one loose yet.
Okay.
Cool. Nope, good question. Let's see. So plugging and chugging, let's see, plus 3,000, plus 21,000, plus 4,000, and then that's divided by. Okay, cool. I wonder what that is. Natural log of that. 9.8 times 300. Cool. So this gives me 5738.424 meters per second of delta V. I always convert that to kilometers per second. It just makes more sense to me. So 5.738 kilometers per second from stage one. Okay, so far so good. Now, for delta V stage 2, I'm going to draw a picture here. This is what can be kind of confusing. In the transition between doing stage 1 and stage 2 math, we assume we have cut stage 1 loose. It fell away. That's the purpose of staging. When you're done with something, you jettison it and go back into the atmosphere. So what that means is our M initial for stage 2 is going to look a little different. I'll show you what I mean. So we have ISP, G naught, same equation, same math. I'll just say M init over M final. Okay, the ISP of stage 2 is a slightly different rocket, it looks like. So that ISP is 350, still 9.8. Natural log of, okay, M initial. We got rid of stage 1, so that structure is gone. So really all we have left is the structure of stage 2, the propellant of stage 2, and the mass of the satellite. Just like before, the M final is going to be basically what's left over after we have burned through all the propellant of stage 2 now. So we'll still have the structure left over. We don't have any fuel. We still have the satellite.
Sir, can you move your paper a little bit to the left?
Oh, is it starting to scooch off? Thank you. Yep.
Yes, sir. Thank you.
Nope, that's good. Cool. Okay, so now I can plug in chug. Beta keeping me honest here. Appreciate you. I think that's who that was. Okay, cool. I've been known to mistake voices on the phone before. It's bad. Okay, let's see.
You're right, sir. Thank you.
I knew it. I knew it. No, that's good. Okay. So 7,000. Beep boop. Okay. Yep. That is good. So we get 4754.99 meters per second. Again, convert that over to kilometers per second. 4.755 kilometers per second of delta V from stage 2. All right, so delta V total, add them. 4.738. Oop, you know what? Plus 4.755 equals plus 5.738. 10.493 kilometers per second for the whole shebang. Nice. Okay, so you really make your money there by keeping track of where you are in the problem, right? That's why I literally always draw myself pictures. So, okay, number 7 says, what is the relationship between the delta V design and delta V total created by a launch vehicle? So, let's go over here because it's actually given to you. Oh, nope, wrong, sorry. Stay over here. On the launch velocity part, there's a delta V design that we calculate. If you guys remember calculating like the south and the east and the zenith, and the V of the launch site and the V of the loss due to gravity. You did all this stuff for the milestone 2 and for the homework. But so reaching back to that a little bit, what's the relationship between those things? Well, in thinking about it specifically in terms of rockets, delta V design is basically how much you could possibly get, I believe, out of a vehicle. So like a delta V design is like how much, all else equal, like everything's perfect in the world, how much thrust could you get? And delta V total ends up being you account for all the things you accounted for, right? The launch site velocity, losses due to gravity, all that kind of stuff. What I think the problem was really meaning to ask is what's the difference between delta V design and delta V needed? And delta V needed is all the math that you did when you were trying to calculate how to get something up out of the atmosphere, right? And then delta V design accounted for this losses other than gravity term, which we gave you as like drag and inefficiencies with the rocket and such like that. So I think that's what the problem really meant to ask. This is a review packet from, I think, at least last year, and this question's from a couple of years ago. But take for number 6, for example, we calculated the delta V total we could get out of that vehicle. And we were accounting for launching a payload. So the delta V total we could get with that big fat payload sitting on top was 10.4 whatever kilometers per second. The delta V design, though, is if we didn't have a payload, everything was perfect, no drag, everything was great in the world, how much could we get out of the launch vehicle? So, yeah, that's the best I can do with that one. I'm trying to guess what the problem was actually getting at, but. Okay. All right. Coffee sip. All right. So now attitude and control. So briefly define what a spacecraft disturbance torque is and give an example of one. Okay. So first of all, let's just think about what a torque is. So if you have a force that's acting at this point right here. You know what? I'll make it an X. There we go. It's going to cause this lever arm to go up this direction, right? That's just what a force is. That's what a torque is. You have a force acting at a distance from a center point. Okay. Well, what's an example of that on a spacecraft? Well, one of my favorite examples is Landsat. NASA's Landsat satellite just has one solar panel. It's not balanced in that way. It just has one giant long solar panel sticking off of one end. So solar pressure, literally the particles coming off of the sun, hit the solar panel and very slowly over the course of months start to tilt the satellite away. So a disturbance torque is any torque that moves satellite off its desired pointing. And the example I gave was solar radiation pressure. Some other examples might be gravity, because no satellite is a perfect sphere, right? They're all boxes with things hanging off. So over time, actually that causes, so for example, if your satellite is bigger on one end than the other, then that means gravity is going to pull that end towards the Earth over time. It's really weird. Also drag. Like for example, Landsat has that giant sail essentially. Now it happens to be flying high enough that doesn't matter, but what if your satellite was like your design project satellite and it's flying low and it's catching a bunch of atmosphere? So anyway, those are some other examples. Okie dokie. So a satellite requires, number 9, a maximum pointing stability of 500 meters. The attitude control system needs to provide a pointing accuracy of 0.03 degrees. What is the maximum altitude the satellite can be at to meet the pointing requirements? Assume a circular orbit. Okay, picture time. What this is saying is we want to know how high the satellite can be so that it doesn't pitch off axis any more than 0.03 degrees. Or put another way, we only want the satellite to swivel within this 500 meter distance on the Earth. This is this really quick, let me make sure there we go, on the camera. D equals H psi. So I'm back over here in the control area, D equals H psi. And I'm solving for height. So this is what it's going to be. But there's a couple of things we have to do first. So this pointing accuracy cannot be in degrees. This equation only works in radians. So let's convert. This is going to be some ungodly small amount of radians, and that's okay. (5.236 times 10 to the negative 4th radians. Cool. So that's actually all we need to do, and now we can plug and chug really easily. So 500 meters over 5.236 times 10 to the negative 4th radians. $954,929 meters. I always convert that to kilometers because it just is how we do business. So that ends up being 954.93 kilometers. So the satellite can't be any higher than that, or else it'll start looking at things it's not designed to. So that's what that's talking about. Ta-da! Okay. 2 passive and 2 active attitude sensors. Okay. Or not sensors. We'll talk about sensors in a second. Actuators. Okay. So actuators are things that make you point the way that you want to point. So a couple of passive ones are gravity, gradient, boom. That's one of my faves. That's where you basically have, like, if this is your satellite with its little solar panels, and it hangs off, basically there's a rod or a string even, and a weight at one end. And because this is closer to the Earth, this little weight, the Earth is going to pull on that slightly more than it pulls on the upper part of the spacecraft. It keeps it roughly pointed at the Earth. It's super rough. Another way so that's passive, right? I literally invested no energy in the system, no fuel, no gas, nothing of the sort. It's just hanging off, being happy. Another passive one is spin stabilization. Again, these aren't the only two, but they are 2 good ones. Spin stabilization is like, for example, you have a satellite like this, and it's kind of a tricky one because you do invest some energy to start it spinning up when you first get on orbit. But after you've started it spinning up, you don't have to invest any more energy because of angular momentum, like a bicycle wheel, right? The whole physics experiment being on that little platform with the bicycle wheel. That's what we would have done in class, but I didn't have you guys in class. But once you've invested that initial startup energy, it just keeps spinning and pointing towards the Earth or wherever you want it to point. So those are two passive ones. Active ones include reaction wheels. Active actuators, we have to actually invest some energy in the system to make it point where we want to point. So reaction wheels, and I'll put control moment gyros, CMGs here as well. Basically giant wheels that you're spinning at a certain rate, and then if you want to change where you're pointing, you increase or decrease the speed at which they're spinning, and it causes the satellite to torque the other direction. So those are pretty cool. But the second active actuator, thrusters, are actually needed to de-spin those wheels, because you can't just keep spinning them up forever, or else they'll literally spin off their axis and fly off the spacecraft. I mean, they can only go so fast. So we'll fire a thruster a certain way so that we can de-spin the wheels and slow them back down to like a sane speed. Call it momentum desaturation. You don't have to know that, but those are some active actuators for you. Boom. Okay. 2 attitude sensors. Well, I'm going to give you 3 because reasons, but kind of in increasing order of precision here. There is such a thing called an Earth sensor, where if you're a satellite kind of staring at the Earth roughly, space is cold. The Earth is a little bit warmer. So basically, the edge of the Earth against the background of space is called the limb of the Earth. It's really weird. You don't have to know that, but like your limb, like your arm is a limb. So basically, the Earth sensor can detect, is it pointing at the warm or is it pointing at the cold? Pretty rough pointing, but it's something, right? It's something. The next sensor is kind of like a variation on that tune, and you have your satellite here. Beep boop. It's basically doing the same thing as the Earth sensor, but it's looking for light instead of heat. It's like, am I pointed off here where I'm seeing dark, or am I pointed towards this giant light source? So again, pretty rough pointing, but it's something more precise, because there's only one big source of light in the sky. It's the sun. The last kind is called a star sensor, which is extremely precise, and it's basically programmed with constellations of the night sky, and it is trying to detect, am I looking at the right constellation? So it's extremely precise. Star sensors are pricey, unreliable, exquisite, but when they work, they're really amazing. So those are some attitude sensors for you. Again, that's not all of them, but those are some of the biggies. I need a coffee sip. Before the signals problem, I need a coffee sip. Okay. This is these 2 problems are the lessons I actually did the video for. I did the video for everything, but that I actually was behind the camera for, in front of the camera, I guess. Anyway, talking about signal strength, I'm a SATCOM guy. It's a big deal to me. So I will try and not give you any information you don't need, but this is an entire class. Like, this problem is essentially the entire class that I taught this semester when I wasn't teaching you guys. I was teaching SATCOM. So this is cool. All right, let's begin. Satellites in a circular orbit with an altitude of 600K. Okay, given the ground station and satellite CDHS specifications provided below, calculate the worst case signal to noise ratio the satellite will experience when it can contact the ground station. Okay, this little word or these 2 words make a big difference. The worst case signal to noise ratio. Time for a picture. You know it. You knew it was going to happen. Okay. So you have your little ground station, right? It's talking to the satellite. This is the best case when the satellite's directly overhead. But you guys know it didn't just get there, right? It had to rise up above the horizon, and eventually it's going to pass back below the horizon. The first time, and this is where my picture gets a little bit limited, but the first time that we could really contact the satellite is out here when it first comes up above the horizon. Call this R max. And I don't like the fact that we use R, because that's usually what we're talking about from the center of the Earth to a satellite. In the signals problem here, that's not what we mean by R. R is just the distance from the transmitter to the receiver. Okay, but anyway, if the satellites move in this direction, you know, it was all the way out beyond where you can see, and then it peeks its head up above the horizon. That's the first time you can contact it. Okay, R max. That is what worst case is talking about. So we're not going to use the altitude. That's a red herring. Like that's tricky. If it said what's the best case signal to noise ratio, we would use that. But worst case makes you use more equations. So that's probably what we're going to ask for, as you can see right here. So let's calculate R max real quick, and then we can get back to everything else. All right. Equation sheet says R max is, let me scooch up. R max is radius of the Earth plus the height, quantity squared, minus 6378.137 squared. And that's going to give us, I don't know, let's plug and chug. Beep, boop, boop, boop. That makes sense, actually. 2830.859 kilometers. So what this really means is when it's directly overhead, it's sitting at 600 kilometers. How nice. But when it's way out on the horizon, the first time we can see it, it's like almost 3,000 kilometers. That's way worse. That's way worse. And why is that a big deal? Because signals get weaker when they travel through space. So the longer they have to travel, the weaker they're going to be. That's the bottom line there. Cool. Okie dokie. This brings us to our first big idea with the CDHS problems, with the signals problems. I'm just going to write it as its own step because it's so important. Convert all units to their SI units. What does that mean? That means kilometers convert down to meters, megahertz and gigahertz, convert those to just hertz. Degrees Celsius, no way, convert that to Kelvin. And if you have like kilowatts, you're going to convert that to watts. So anything, basically everything in its most simple units, right? Meters, hertz, kelvins, kilograms, everything that is the most simple of it. And no mega, no giga, no anything like that. So my R max equation came out in kilometers. That's why I'm getting at this. So what's that in meters? You guys see how I did that? Just multiplied by 1,000 to get meters. Good. That's our R max. So let's go do that with all our units right now. Okay, all these terms are going to make sense in a second, but the bandwidth of the receiver. So basically bandwidth is, in a signals term, it's like how much of the electromagnetic spectrum are you actually using? So for example, if our signal bounces around between 200 megahertz and 202 megahertz, the bandwidth is 2 megahertz because it's the difference between the low signal and the high signal. Ask me again about that. Never, unless you want to take my SOCOM class. But that's what bandwidth is essentially. It's how big a pie chunk of the EM spectrum are you using? And they gave it to us in megahertz. I am not fooled. I will not be tricked. Mega means 10 to the sixth, so I'm going to just say that's 2 times 10 to the sixth hertz. Okay. Temperature actually matters. Temperature is what we call a noise term. So this is weird, but noisy antennas are hot antennas are noisy antennas. So like ideally, I would have a super cooled antenna and it was always chilly and cold. But that's never the case, right? It's sometimes hot. What if my antenna is directly in sunlight? actually decreases the effectiveness of your antenna. It's very weird. Again, I have a whole class if you want to ask about it. But basically, temperature is given to us in Celsius. You are given in your equation sheet the conversion from Kelvin to Celsius, so just plug and chug that. It says we should just add 273.15, and that'll give us the Kelvin version of the temperature. Good. Now gain, just so you guys know, gain is a term we could spend a long time on. We could spend multiple classes on, and I do. But it's essentially how efficient is your antenna. So like if I don't know if anyone's car has this anymore, but it used to be that there was these, whip antennas on cars. They're just like a long pole, just like a long rod. And some cars would even extend them and like contract them for you manually. And people would drive, through drive-throughs, and they would break off their cars. And anyway, that's what we call an isotropic antenna or a dipole. Anyway, point is, you guys have also seen, by contrast, giant dish-looking antennas, right? Look like they're basically a bowl. That's a way more efficient antenna. You can actually focus your power way better. So higher gains are good. Lower gains are not as good. And antennas that are shaped a certain way, like a bowl or a dish, are way better at focusing signals, and that means they have higher gain. So, okay, I just wanted you to know, because a lot of these terms are just weird, and you never encounter them in real life, so I just wanted to explain them. Okay, gain. So gain is a unitless number. It's got no units, so we can keep gain as it is. Receiver gain of 5, transmitter gain of 10, those can stay as they are. Okay. All right, so that's all the ground station antenna, the kind of the factoids about it. The satellite, in this case, has a transmitter power of 15 watts. That is pretty weak, but kind of common. And it's in watts. It's not in kilowatts or megawatts or anything, so we can just keep that as 15 watts. That's good. Gain, again, is unitless. You can just leave it as it is. Transmission frequency. Okay, transmission frequency, 2.5 times 10 to the 9th hertz. What I usually see is it's given like this, 2.9 gigahertz, and you have to remember to calculate it over to just normal hertz. But they were nice, and they just gave us the amount of hertz here. So right on. All right, we have almost all the units that we want. I'm looking over here at the equation, and I see that we aren't going to need frequency. We are going to need wavelength. So handy dandy, all the way back in the remote sensing area, we can get wavelength if we have our frequency, and we do. So I'll just do that here. Wavelength equals C over the frequency that we were given. Oh, I keep scooting the wrong way. Okay. C is the speed of light. I don't think this is on here anywhere. There was a version of the equation sheet where we did have it on here, but speed of light is 3 times 10 to the 8th meters per second. And the frequency that we were given of the signal itself is 2.5 times 10 to the 9th hertz. So when we plug and we chug, E9, boop, I get the wavelength of my signal is, I don't know, 12 centimeters, 0.12 meters. Pretty small. But that is common for that size of a signal. So, okay, I just wanted to set the stage. Again, like, it's not going to take you this long, by far, not going to take you this long on the test. I just wanted to walk through what all the terms are, because it's basically a giant fire hose of acronyms. And you're like, what the heck is actually going on with signals? I have no idea. Well, that's what all the terms mean. So your big steps are, make sure you do Rmax if it says worst case. Convert all your units to SI, and then you can plug and chug. And so let's do that very thing. Signal to noise.
Sir, the C is under remote sensing payloads on the equation
great.
sheet.
Oh, I'm looking right at it. Thank you, ma'am. Is that Cassidy? Yeah. Thank you, ma'am.
Yes, sir.
Okay, so you don't even have to remember that. That's good. I always had it memorized from physics, but okay, good. So under remote sensing is your wavelength equation and C. I looked right at it. If it was a snake, it would have bitten me, as my mom always says. If it was a snake, it would have bit you. Okay. Cool. So you don't have to remember. That's even better. Alrighty. Let us begin. So first of all, the equation that I'm using is this: signal to noise equals huge gobbledygook mess. I'm just going to switch the order of these two terms because that is more convenient to me. So let's write it all out. First things first. Signal to noise is the power of the transmitter times the gain of the transmitter. We abbreviate transmitter as X-mitter over K times the bandwidth, right? That chunk of the spectrum, times gain of the receiver. Remember we said gain was just a number that says how efficient your antenna is, okay, over the temperature. And I'm going to put this squared term last because it gets really complicated if you leave it in the middle. So don't forget squared. In fact, don't forget it. Okay. My heart aches for you guys on this problem because it's so rare to see somebody get full credit. Almost everyone gets most credit. But to get full credit, you have to just be as meticulous and anal as I'm trying to be here, with all the units being exactly right, not forgetting your squared, plugging everything in correctly. It's kind of a little bit of a monster. There's no reason it has to be, though. It's just that units usually get forgotten along the way somewhere. And you get really close, but not quite all the way. But you guys are going to get all points because you're my class. So, ha. All right. Okay, so let's start plugging and chugging. First things first. We did all our hard work basically already. Power of the transmitter. Okay, transmitter power. Power of X-mitter. 15 watts. Let's plug and chug. Gain of the transmitter says 10. Okay, I'm going to have to scooch this out a little bit. K is a constant. It's right here. 1.381 times 10 to the negative 23rd joules per Kelvin, if you're interested. 1.381 times 10 to the negative 23rd. I believe it's Boltzmann's constant. I'm going to have to double check that one. But either way, it's provided for you right there. And then the bandwidth, 2 times 10 to the 6th hertz, like we found from above. Okay, that takes care of this term. Now, I'll just underline it like this. Now let's do this term. Gain of the receiver. Receiver gain is 5. Over the temperature, which receiver temperature we discovered was 293.15. Okay. Now for this last term. I'm just going to put the squared right there so I don't forget it. So the wavelength, am I still visible? Cool. Wavelength is 0.12 over 4 pi times, in meters, our R max. So 2.83085 nanner. Whew. So what I like to do here is go term by term by term and just multiply them. So that's how I do this. And depending on your calculator and your comfort level with that, it's up to you how you want to do it. Another way of doing it is doing the entire top and then dividing it by the entire bottom. Again, you guys can do it however you like. The interesting thing about that, as a side note, all the things that make a signal better are on the top. Power and gain and wavelength, okay. And all the things that make a signal weaker are on the bottom, right? How much bandwidth you're using, how hot the antenna is, and how far out it is, right? The R max versus R min. So anyway, however you want to do it. I'm going to do it term by term. 15 times 10. 23, 2e6. Boom. All right, that's one term times 5 divided by 293.15. Okay, now times, okay, this is tricky. 0.12 divided by 4 pi 28. What was it? 3085. 859, boom, squared. Is one of you guys buzzing me? No. Okay, cool. So make sure. Aha, okay. So what I finally got out of all that, and this is the answer, which I'm grateful, because again, there's a lot of math error risks here. I got a signal noise ratio of 1.054. No units. It's a ratio. There's no, well, you know what? I'll just, the units are technically decibels if you convert it to decibels, but that's not what we're asking you guys to do for this class, so you can brain dump that piece of knowledge. So for you guys, no units. And what's the big deal? Like, it's hard to put your hand on a signal to noise ratio and be like, ooh, that's good. Like, you can't hold it. It's one of those concepts. But if your signal to noise is greater than 1, that's what you want. Because what that means is the signal is slightly stronger than the noise. In real life, we want SNRs of like 10 or greater. That'd be nice, right? If you have an SNR of 1, technically speaking, you can barely hear the signal. But that's okay. Oh, and I realize I'm at the end of the hour. So if you got to drop off, please, feel free to. But I'm going to keep going until this is done, and then the recording will be posted. So anyway, okay. So we'll press on here. So this is a the worst case SNR is out on the horizon. I can barely start talking to the satellite, which is fine. The good thing is, as it gets closer to arm in, it'll get a lot better. So, okie dokie. So number 13 here. Let's press on. This is all about taking an image and how many of these images can I transmit during the time when I can see it to the time that I lose contact with it again. So we call that a pass. That's the overflight of a satellite. It's a time. It's an amount of time. Okay. So it's saying that this satellite collects pictures that look something like this. It says they're like 13,000 pixels, 13,500 pixels. Nope, 500. I don't know where I got that from. 13,000 pixels long by 1,500 pixels wide. So like a long strip. And has tons of little pixels, right? Pixel elements. Picture elements, rather, is what a pixel means. And each one of these pixels needs 12 bits of computer code to describe it, like what its color is and all that. So we're told that also our data rate is 2 megabits, and I didn't actually say that wrong, 2 megabits per second. So what the heck is a megabit? Well, coming up here to our unit conversions, it's a binary prefix. So what that means is it's a literal number of bits. So 2 megabits per second is 2 to the 20th bits per second. That's what our data rate is. So 1 megabit is 2 to the 20th bits. This is where I kind of register my frustration with teaching this. This is an engineering way of talking about bits. To be quite honest, as an operator, I've never used this. And when you buy your hard drive, you don't use this. Like your computer doesn't use this. In real life, you just don't use this. What's your Netflix downloading speed? Oh, I'd like to have 100 megabits per second, please. They'd be like, what? We don't offer that plan. We're talking to Comcast or whoever your provider is, right? But it's a way that engineers describe an absolute number of bits instead of doing the whole bits and bytes thing. So, all right, public service announcement over. But our data rate is 2 of these 2 to the 20th every second. Great. So how many images per pass can I get if one pass is 10 minutes long? Woo. Okay, well, I'm going to start over on the left here. Let's just see how big a picture is. One picture is 1,500 pixels by 13,000 pixels. And that we're told there's 12 bits for every pixel. So let's see how many bits are in an image. Again, this all becomes like a unit canceling game. Okay, I get that there are 234 million bits in every image. And I'll just stop here and, well, not stop here, but just pause here and say, there's not an equation on the equation sheet for this kind of problem. When you see the data rate transmission thing, it's literally just kind of a logic game. And it's the same thing that you would do if you're a nerd like me and you're interested in how long it takes your Netflix file to download, right? It really is just a logic mind game. How big is the thing? Well, how big is the data rate? Well, do the math and find out. And that's essentially it. There is no equation for it on the equation sheet, just to kind of let you guys know. So what I do is find out how big a picture is first, and then how much of that could I transmit down to the ground station every second, and then how many seconds do I have. So I guess you could say this is my step 1, this is my step 2, and this is my step 3. So, okay. I probably should have let off with that. All right. So, okay, we have 234 million bits per every image. That's great. I want to find out how many images I can transmit in a second. In just 1 second, how many images can I transmit? So what I'll do with that is, let me try and kind of divide this out here. All right, that's step 1. This will be step 2. Okay. So 2 to the 20th, 2 times 2 to the 20th bits per second. I want to cancel out, let's see, I want to cancel out bits. So I will put bits on the bottom. Bits cancel. Now I have how many images I can transmit in a second. Let me do that math here. Divided by 234, 0, 0, 0, 0, 0, 0. I can transmit 0.00896 of an image every second. Well, that makes sense. These are big images, and I have like 10 minutes to transmit as many as I can. So, okay, so if that's how many images I can do in a second, now I want to find out how many images I can do in a pass. So there are 10 minutes for our pass. I would like to have that in seconds so I can actually have the units work out. So obviously 1 minute has 60 seconds in it. And then, let's see, images per second. I want seconds to cancel out. So I'll multiply that by 0.00896 images in 1 second. Cool. All right, so that gives us 5.378, no, 377. Images per pass. Woo! That's not that many images, but the images are really huge. So anyway, that's something we satellite folks have to think about a lot, because you could take a bazillion pictures on your with your satellite as it flies across the Earth, but you're going to run out of hard drive space if you don't download them quick enough to free up some space. So, okay, let me make sure I'm visible here. So anyway, there you go. The question might ask how many whole images. And that's just saying how many complete images could we get in a pass? Well, we could get 5 whole images and then 0.377 of the next image. So depending on what the question asks for, either of those would be correct. Whew. Okay. I am going to pause here for 60 seconds. All right, let's keep pressing on. Appreciate you guys sticking with me. Again, it's up to you. We're after class time now, but great to have you guys with me. Okie dokie. 3 energy sources that can be used to power a spacecraft. Everybody could think of the first one, obviously, solar power. That is the biggie, really. I mean, any spacecraft that stays within the orbit of Jupiter, we're going to use solar panels for. Now, out beyond, we're going to use a different type of power that I'll talk about in a second. But batteries are the second source. And you might say, well, I thought the solar panels were just charging the batteries. And that's usually true. That's how most satellites are built. The subtle difference is very few satellites only have batteries. And a good example of this is FalconSat. Well, actually, it was Falcon Gold is what it was called. Our very first cadet-built satellite that we launched from USAFA, built at USAFA, launched from Cape, I think. Either way, it just had batteries, and it only lasted in orbit for a couple of weeks, I think. And when the batteries were done, the mission was done. And why did we not put solar panels on it, you might ask? It's like, well, it was our very first satellite. It's a lot simpler just to put some batteries inside and do a quick mission as a proof of concept. So it is possible that you only have batteries for a satellite, but that means that they are going to run out of power at some point, right? The last thing I want to talk about is a radioisotope thermal generator. If we're going to send a spacecraft out beyond Jupiter, like New Horizons, which is going to Pluto, or something like that, or Voyager, right? The Voyager probes. They had basically a hot radioactive, hot radioactive rod. And then these strips along the side, which convert the heat to electricity. And basically, as you guys remember maybe from physics, the half-life of something radioactive, it decays over time and it's emitting radioactive photons, essentially, into other particles. But the little strips, the thermoelectric strips on the side, are taking that heat and generating electricity from it. It's a very little stream of heat, and it's kind of like a very epic battery. It's like it is going to run out of juice at a certain point. But to give you some perspective, the Voyager probes launched in the 70s, and they're still beeping. They're out beyond what we call the heliopause, which is the edge of the sun's magnetic influence. It's really wild. But they're still working. But the trick is we have to keep turning off instruments because we're slowly losing power on the RTG for those probes. So,
Sir, can you
anyway,
say that one more time?
Yeah.
One. Just like what it's called.
Yeah, it's called a radioisotope, one word, radioisotope thermal generator. Actually.
Thank you.
Yeah, you're welcome. Let me actually double check something real quick. Radioisotope thermoelectric generator. I knew that I was missing a word in there. Radioisotope thermoelectric generator. Yep, and that's how we power all our probes out beyond Jupiter. All the way up to Jupiter, you can still get away with solar panels. That's the reason I keep saying Jupiter. But beyond that, the sun is too weak. So, all right. Let's continue. All right, let's do the math for this. A spacecraft is carrying a payload requiring 500 watts. They'll be turned on, in the sun only. That's going to make a difference. The bus requires 1,200 watts, and it runs continuously. That's going to make a difference. If a spacecraft is in a circular orbit at an altitude of 800K around the Earth, what is the solar panel power required? Okay, so first things first, I go over to my electrical power part of the equation sheet, and thankfully, you can kind of just march your way down this part of the equation sheet and get to the answer. It's not like the whole flipping, trying to find the equation. This part is really self-contained, and you can get the points on this really quick and easy. So, as always, I think a picture helps. It sure helps me. So here's our situation. Sun, Earth. Here's our spacecraft's orbit around the Earth. And the Earth casts a shadow, right? It's in direct sunlight, obviously. This is us right now, right? On our side of the Earth, we're facing the sun. But there's this area here that is in shadow. So as our spacecraft goes around, it's going this direction. It's all good. It's collecting lots of, solar panel power happily in the sun. But then we're going to have to account for what happens in the eclipse. We're going to have to run on batteries for a little bit. So that's kind of what we're asking here. The first thing we're going to calculate is this thing called rho. Looks like a P. It's like a Greek letter P, but it's called rho. And rho is, and this is where I start to run out of ability to draw because it's really small. But it's the half angle that the spacecraft spends in eclipse. So basically the total angle that it spends in eclipse is 2 rho. But yeah, the portion of the orbit as far as an angle goes that it spends in eclipse, that's what we want to find out first, because that's going to give us our time spent in eclipse, and that in turn is going to give us our energy that we use during eclipse. So, alrighty, let's start plugging and chugging. The first thing that I like to do, actually, this is fine. We'll just press. Rho equals inverse sine of radius of the Earth over radius of the Earth plus the height or the altitude, which we were given right here. Oops, and I managed to cross it out. But first, make sure your calculator is still in degrees. This problem uses degrees. All right, cool. Let's press on. So inverse sine of 6378.137 over 6378.137 plus 800 equals. Oops. There you go. Cool. Inverse sine of that is 62.69. I'll keep one more degrees. All right, so that's the half angle. So 2 rho is, boy, it's going to spend more than like 120 degrees worth of its orbit in eclipse. That's plenty. That's good and plenty. All right, so let's find the time in seconds that we spend in eclipse. So that is 2 rho over 360 times period. Oh man, where's period? What is period again? Well, period is all the way back on this side. Oops, make sure I'm visible, sorry. Period's over here under two-body equation of motion. That was way back in January before we even thought Corona was a thing. Oh man, those are days. But 2 pi times a cubed over mu. All right, so now we can plug and chug. 2 times 62.692 over 360 times 2 pi a cubed over mu. So a being some major axis. We have to be careful not to use just altitude or anything like that. I was running out of space. This is my problem in life. All right, over mu. Haven't used mu in a while. Shoot. Okay, now what does that end up being? Time in eclipse equals.
Wait, sir, sorry, what did you plug in for A?
I plugged in, so remember, and this goes, way, way back, but so you have the Earth, and, this is if your satellite's here, sorry, I should have drawn that bigger, but there's the height above the surface of the Earth, and then you have to add in the radius of the Earth.
Oh, okay.
So basically, semi-major axis is the radius of the Earth plus whatever your altitude is, which is usually abbreviated as h for height. And that is that anywhere up here? No, that's one of those things we make you guys remember. So that's semi-major axis is radius of the Earth plus your altitude. And height is just your altitude above the Earth, above the surface of the Earth. Does that make sense, Veda?
Yes, sir. Thank you.
Cool. Yeah. Yeah, it's hard to see it. I ran out of space, but all right. So starting off with that, or let's see, times 2 divided by 360. Okay. Multiplied by 2 pi. Multiply that by, oh man, I should have worked this the other direction, but that's okay. Square root 6378.137 plus 800 squared divided by parentheses all over the place, man. That is not correct. All right, let me try again. I knew I should have worked it the other way. Cubed. Square root of that. There we go. Divided by 360. There we go. Oh, geez, man. Okay, so the time we spend in eclipse, I get 2107.988 seconds. Awesome. So that's how much time we spend in the dark. I'm afraid of the dark. Satellites are afraid of the dark, obviously. So back to our EPS side here. Oh, scooting over so you can see it. Okay. Now, all right, we found rho, we found TE. Let's just move down to energy we use in eclipse. So the energy that we expend, which by the way, it's all going to be battery power, right? It's going to be the power that we use from the payload plus the power that we use from the bus, all times the time that we spend in eclipse, which we just found. Now, this is why in the sun only matters. So some payloads, like for example, if you just had an optical camera, that is almost no good in the dark, right? I'll go ahead and just say it's no good. So if it's not turned on in the dark, that means we're not using any power. So really what this equals is just power from the bus, 1200 watts, times the time we spend in eclipse. 2107.988 seconds. Sorry, I shouldn't keep leaving units on or off. Just be consistent here. All right, so this is going to give us a weird unit called watt seconds, but that's okay. So I get 2529585.884 watts dotted with seconds. What's a watt second? Well, it's a cousin of the unit that the electrician comes and reads on your electricity meter. Usually those are in kilowatt hours instead of watt seconds, but it's basically a power dotted with the time. Anyway, so the energy we use in eclipse, it's a unit of energy, is this many watt seconds. Okie dokie. Let's go ahead and use that for the energy we spend in the sun. So the energy we expend in the sun is going to actually be more. Why? Well, for one thing, the payload is turned on now. And I think we'll find that we spend more time in the sun than we do in eclipse, right? You can even tell that just from the picture. Even though it's a crappy picture, you can say that there's more circle exposed to sun than there is behind the Earth. So what is the time in the sun? Now, you don't have an equation for that on the equation sheet, but a satellite is either in the sun or it's in eclipse. So the total time that we spend is, well, let me put it this way. This might make a little more sense, actually. Oh, scooting. One period, a total orbit, is going to consist of either time in the sun or time in eclipse, right? But you add them together and you get a full orbit. We know time in eclipse. We can find out the period. I didn't, we found it above, but I didn't solve it for its own sake. So time in the sun is going to be 2 pi a cubed over mu, which is the period. Again, we solved for it up here. I just didn't solve for it on its own. Right, so period minus the time we spend in eclipse is going to give us the time we spend in the sun. So now I must plug and also chug, as one does. Let's see here, 2 pi times square root. 8.37 plus 800 cubed divided by mu times 2 pi. Okay, so the total period being, 6052 seconds minus time we spent in eclipse, which was 2107.988. So 3944.425 seconds is how much time we spend in the sun. Whew. Okay. So the energy we expend in the sun includes our payload, which is on in the sun, 500 watts, plus the bus, which is always on, times the time we spend in the sun, 3944.425 seconds every orbit. So that's going to be quite a bit more, I think, than the energy we use in the eclipse. So 6705522.683 watt seconds is how much we expend in the sun. It's so much more. It's like more than twice as much as we expend in eclipse. And the reason is when we're in the sun, we not only have to run the payload, we also have to recharge the batteries that we use during eclipse. So that's a big deal. Okay, finally, we get to solve for PSA required. That's what we originally wanted. PSA rect. Power of the solar array required. That equals the energy that we expend in eclipse plus the energy we use in the sun, all over the time we spend in the sun. And again, why is it just over T sub sun instead of T sub sun plus T sub eclipse? Well, solar arrays are only giving us power in the sun. Duh. But it's like so intuitive once you think about it. You're like, oh shoot, yeah, that's where the solar panels are actually giving us power. So, okay. I might run out of space, but I'm just going to try it anyway. So 2529585.884 plus 6705522.683. All over the time we spend in the sun, which is 3944.425. Let's see here. 2529585.884 divided by. All right. So the solar arrays have to produce 2341 watts. I want to double check that with the answer key. So I recall that is correct, but yep, cool. Yeah, Yeah, 0.3 technically watts. Whew. Any questions from y'all on that? I know that's kind of a wild one, but not so bad really, because you just get to go all the way down the equation sheet really methodically. So,
Sarah, is there any way that after the review is done, you can post pictures? Because some of it is kind of blurry.
oh, okay. Actually, what if I did this? Does that help any?
I think it's more just like when you're writing, it gets kind of blurry just because there's movement. And most of it is easy to follow along with, but some of it I just can't read. So.
Oh, okay. Yes. Pictures. As in pictures of like, oh, I see what you're saying. You know what I could do? What if I scanned this back in?
Yeah, that would be great. That would be super helpful.
Okay, and then you could see it as you're watching the video. I think you'll have to call me on this if it's right or wrong, but I think once Teams actually mashes all the video together and posts it, it'll probably be a little clearer. And as you're watching me do it in person, though, like it's kind of crappy. But even in the event that that's not true, it's super easy. I'll scan this back in, and then you can follow along.
Okay, awesome. Thank you so much.
Let me take a note. Yeah, no, you're welcome, and thanks for letting me know.
Yes, sir.
When I was actually making the videos, I would record them with a different like piece of software. Teams is not the best for it, but it does help everybody see it all at once, which is kind of cool. So let's see, upload, scanned, doc. Okay, note taken. Alrighty, number 16. Briefly explain what a battery's depth of discharge is. Wow, I just can't talk at all. All right, so if you imagine a nice battery and it has all this capacity, man, look at all the electricity that it can make. But you only ever discharge a little bit of it. That's the depth of discharge. I'm going to give a different and better example, but so with your cell phone, if you're anything like I am, you use like half of it and then you throw it back on the charger. Like you get your battery down to like 50% and then it goes back on the charger. And that's pretty common for me. Like as soon as it gets low-ish, I start to throw it back on the charger. So what I don't do is, just because I'm anal about it, I guess, is I don't drain the battery all the way and then charge it back up, because then you're tied to the charger, right? So if I only ever use half of my battery before charging it back up, my depth of discharge is 50%. Or put another way, some folks like almost never let the battery get low and they just like discharge it maybe 25% of the way, right? They get down to like 75% and they're like, put it back on the charger. So in their case, their depth of discharge would be 25%. So in the context of satellites, it's the exact same thing. Their charger is being in the sun with solar panels. All right, the Earth is casting the shadow. And as soon as my little satellite comes in, it starts discharging its battery. Now, you could design a satellite that basically takes the cell phone all the way down to zero in its eclipse. Like you could use a smaller battery, it would be cheaper, it would be lighter. But the reason you might not want to do that is, what if after I come out of eclipse, my satellite isn't pointed the right way and I'm not generating any power from the solar arrays? That means your satellite's going to be off for a while, and it could even threaten the health of it. You might not even be able to turn it back on. That actually happened with, I believe, with a NASA satellite. It came out of eclipse, and they're like, okay, right on, like I'm rooting for you, start charging up, but it was pointed the wrong way, and it could barely get any power, and it was never enough to turn the satellite back on. So you don't want to do that. And I'm not saying NASA designed it wrong. I'm just saying there's a risk when you come out of eclipse that you're still going to need to use the battery a little bit. So what you do is use a battery that's big enough so that in eclipse, you don't drain it all. You just use some of it, right? Here's all this potential, like it's charged up and you only use this part of it. So in my crappy drawing, it looks like maybe I've used 30%. That gives you some reserve if you have to come out of eclipse and still use the battery. Anyway, all that to say, depth of discharge is how much as a percent or a ratio, right? A decimal, do you discharge the battery? That's what depth of discharge is. So again, that's me explaining it to you. You wouldn't have to do that much on a test. I'm just trying to make sure I explain it well. You could just write this part. Okay, the thermal part, the thermal stuff. So this section is all about, I want to keep my satellite at a certain cool temperature in the sun, at a certain warm temperature in eclipse. And the temperature swings are wild. They're really insane with the satellite. So you actually have to put a lot of thought in. This is what you guys are going to do for milestone 3, is design all 6 sides of your satellite so that they're radiating just exactly as much heat as you want and no more and no less. So that's the game we're going to play here. So SquareSat. That's the lamest name so far, but it's not the worst. SquareSat is a cube-shaped satellite that measures 0.3 meters on each side. Okay. All right, and you know me. Here comes the picture. Cube is, I really struggle to draw a good cube. Well, that's not the worst. Okay. Sun's over here. Earth is here. And it's orbiting, right? Okay. So, heat sources. Well, I just want to think about this for a second. Your satellite, when it's in the sun, is receiving direct sunlight, obviously, right? So this is sunlight, or what we call solar input, and that's 1358 watts per meter squared. Okie doke. Also, when the sun radiates the Earth, some bounces back out. Call that albedo. And that always sounds like an Italian dressing to me. Like you could have chicken albedo instead of chicken Alfredo. I don't know. Either way, that's 407 watts per meter squared. And, I'm going to get rid of that so I can draw the last heat source, which is directly radiated off the Earth to the satellite. That's called Earthshine. Just by virtue of the Earth being warmer than the background of space, which is extremely cold, the Earth's got a molten core. It's nice and pleasant on the surface, so there's a little bit of heat coming off of the Earth itself, and that's called Earthshine. So you don't have to remember that. It's right here under the environmental control section. All those are listed out for you. First big thing. The assumption here is that all the heat is hitting one side of the spacecraft only. Now, engineers for Lockheed and Boeing and all those satellite contractors have to do the actual math of figuring out, well, the bottom's taking 21.7% of the heat and the top's taking this much. We're not going to do that. We're going to assume that all the heat sources are hitting one side of the spacecraft, and I'll show you why that matters in a second. Okay, so you have a perfectly cubic satellite. That's nice. And each side is 0.3 meters. So let's calculate what the area of one side is. 0.3 times 0.3 should give us 0.09 square meters. Okay. This is not a very big satellite. The payload requires 5 watts of power, and here it is again. This whole thing, it's only on in the sun. Nice. The bus requires 25 watts of power, and let me guess, it's on all the time. How did I know? Assuming each side has an absorptivity of 0.3, so absorptivity is how much does the spacecraft hold on to as a ratio. So how much does it suck in, basically? How much does it radiate away? That's emissivity. So we want to know that the equilibrium temperature in the sun. So what we're going to be striving for here is T sub cube. T sub cube. So first step, we want to find out how much heat is coming into the satellite. That's called Q in. In the second step, we're going to find out how much heat the satellite has to get rid of. Turns out that's all the heat coming into it, plus all the heat of the internal components, like the computers and the wheels and all that stuff. And then we'll solve our equilibrium temperature of the whole cube. Ta-da! All right, so let's do that. Q in, our equation sheet tells us Q in is our heat input. Times the area of one side, again, we're assuming only one side, and times the absorptivity of that side. So what's our heat input in the sun? Okay, this is what matters. We are currently in the sun. So that means we're going to take direct sunlight, albedo, and earthshine. Lots of heat coming in the satellite. Area of one side is 0.09, and of course, we're out of space, but absorptivity is 0.3. The Q in, so the heat going into the satellite from outside is, drum roll, 54.054 watts. Okay, great. So the heat then that we have to get rid of if we want to reach equilibrium, remember, equilibrium is defined as where the heat in is the same amount as the heat out. Because if there was an imbalance in this term or this term, we'd either be heating up or cooling down out of control. We don't want that, because either we'll freeze or we'll burn. That's never good. Okay, so anyway, that's why I set Q out equal to those two things, because we want an equilibrium temperature in the sun. Sweet. Let me make sure. Keep scooching off the wrong way. So the Q in, which is all the heat sources coming in from the outside of the satellite, is 54.054. Now, plus the heat generated by these internal components, right? The computers and the camera and all the payload worrying about and all the computers doing their thing. It says the payload is on in the sun. So we can add that power. And it says the bus is always on. So 25. So you might say to yourself, well, okay, so the payload's using 5 watts of power in the sun. Does that mean it's just generating 5 watts of heat? Just it's converting electricity to heat for no darn reason? And in Astro 310, for the thermal control problems, the answer is yes. In the real world, the answer is obviously no. Like it's doing something that it was meant to do, taking a picture or sending back data or something like that. That's what these systems are actually there to do. But you're going to assume that when it says the payload requires 5 watts of power, it's converting all that power into heat. And you calculate that within Q internal. So I just make that distinction. Like in the real world, you don't just have components making heat for the heck of it. They're obviously doing something, but for Astro 310, you're going to assume that they're converting all that energy into heat. So, okay, so our Q out, the satellite has to get rid of at least 84.054 watts of heat. Okay, so having said that, we're going to use our T cube equation. Man, I cannot keep this straight for the life of me. It's going to be the 4th root of Q out over sigma, which lowercase sigma is this constant that we're given here, 5.67 times 10 to the negative 8th. I believe that's Stefan Boltzmann's constant. I have to check the name, but it's given to you. The area of one side and the total emissivity. Ah, this is what's tricky. So that's assumption number 1. Assumption number 2 is that all 6 sides of spacecraft radiate heat away. And the reason that's a big deal is we were told what the emissivity of one side is. We're going to have to multiply that by 6 because all 6 sides of the spacecraft are venting heat. They're getting rid of heat for you. And again, is that even a real assumption? No, not really. That's another Astro 310 assumption. But remember, only one side of the heat, one side of the spacecraft is absorbing heat. That's our first assumption. And you can make that assumption. You should for Astro 310. Assumption 2 is all 6 sides of the spacecraft are getting rid of that heat. Okay, so let's do the math here. 4th root of Q out is 84.054 over, oh boy, 5.67 times 10 to the negative 8th. Area of one side is 0.09 times emissivity total, which is emissivity of one side times 6 sides. Ta-da! Time for math. Oops. Some ridiculously massive number. It's okay, we're going to raise it 4th root. I get 287.826 Kelvin for equilibrium temperature in the sun. Okay, just remembering our assumptions. Oh man, and I totally scooted that off the screen. Sorry, there we go. All right, now we're going to basically kind of reverse that process to find what our equilibrium temperature is in eclipse, or rather to find out how much emissivity we need to maintain a given temperature in eclipse. We could do the same thing. You could see a problem that says, hey, in eclipse, find out the equilibrium temperature if everything is the same. And we could do that, right? We would turn the payload off. We would just rerun the numbers with no payload and no sunlight and no reflected albedo. But it's not what it's asking. It's kind of putting a spin on it for you. It's like, okay, we want T cubed to be 18 degrees Celsius. And you guys know to immediately get rid of Celsius and convert that to Kelvin. Celsius never works in this class, so do not be taken in by that. Okay, we want the temperature of our cube to be 291.15 Kelvin. We want to know what the total emissivity is. So remember, emissivity total, we calculated up here by multiplying by all 6 sides. So all the problem wants to know is what's the total emissivity of the whole box, of the whole cube, to maintain this temperature. So, okay, well, we are going to have to do a couple of similar steps, right? We're going to have to, first of all, do our Q in, find out how much heat is now coming to the satellite. We're going to have to find out what our Q out is. And again, because it's an equilibrium temperature, it doesn't say equilibrium, but that's what it's asking for. Q in, Q internal. We'll have to run that calculation again. But then for step 3 here, we're not going to find out T cube. We're going to come over here. Oh, I wonder if you can see. And look at Q out. We want to find Q out. We want to rather, I'm sorry, we're going to find Q out. And we're going to use that to solve for emissivity total. That's what we really want. So that's the equation we're going to use. AT4. Okay, we'll come back to that in a second. All righty, picture time. We're in eclipse, so that means our satellite is squarely in the middle of this shadowed region. So my question is, are we getting any sunlight directly? No. Are we getting any reflected sunlight? No, because we're behind the Earth. All we're getting, and of course you can't see it because I drew it too small, but Earthshine is our only heat source. So I'll write out the equation again. Heat input times A times absorptivity. Remember assumption number one, only one side's absorbing the heat. So let's see. Earthshine is 237 watts per meter squared. And again, we're not taking any sunlight. We're not taking any albedo because we're behind the Earth. The area is the same because it's the same satellite. Absorptivity is the same. So that means the amount of heat that we're actually taking in is much, much smaller, which makes sense because we're not in the sun. 6.399 watts. Q out now is going to be Q in, which is 6.399. Plus Q internal. So is the payload on? No, it says the payload's only on the sun, but the bus is always on, so we can at least say that it's using 25 watts. That means the satellite has to at least get rid of 31.399 watts of heat. So now that we have our Q out, we can solve for emissivity total. What was that? 291.15 to the fourth. All right. Now we want an emissivity total of, it should not be a huge number in the hundreds or anything like that. Good. Yep, good. Yeah, it should be like less than 5 for the total, and the emissivity of one side should be not very high. But anyway, we get 0.856, and it's unitless. So, whew, that's really good. That's what it should be. All right, so all that to say, remember your assumptions. Only one side of the spacecraft is taking heat, but all 6 sides are radiating it away. Okay, almost there. Coming down the home stretch. I'm just going to talk through number 19, since writing it is probably not legible anyway. So why is the launch environment the harshest environment a satellite will face? Well, when a satellite gets to orbit, it does face a lot of different forces and things that try and degrade it, right? There's solar radiation, there's micrometeoroids, there's other spacecraft, there's all kinds of things that the satellite goes through, heat changes, right? However, all of those kind of pale in comparison to that vibration that it goes through when it's being launched. A satellite is just a computer in the sky, and to kind of make a silly example, if you stood out on the terrazzo and like raised your laptop above your head and just start shaking it, like after your last final or something, you'll hear parts start to come loose right away, right? You really have to design computers to survive the launch environment. Otherwise, they are not equipped for that. I've seen in a satellite test myself, which is really cool in grad school. I saw we have this thing called a vibe table, and you basically bolt down your satellite before you launch it, and you're like, okay, let's see if it can survive this amount of vibration that the launch vehicle is going to put it through. And it ends up being, what are the kinds of things I saw? I saw screws literally unscrew themselves, like without any, it just, as you start to vibrate it up more and more, screws come loose, they undo themselves, which is really weird. If anything is glued in place, the glue breaks unless it's a really special epoxy glue. Metal bends. And things start shuffling around. Any loose bolts that come loose start to rattle around and just destroy things. So anyway, we know how to beat that. You just have to be very meticulous in building your satellite. So nothing on orbit, short of colliding with something big, is going to treat a satellite the way that the launch environment treats a satellite, which kind of leads us into the next couple of problems. So what you see in a satellite test like the one I was watching is the amount of like things coming loose and destructive interference that happens. Basically, just kind of for fun, over time you have, if this is your time axis and this is your frequency, you have really intense, like over time spikes that, like at a certain frequency, you get all kinds of just destruction here, and destruction here. But anyway, those are called resonant frequencies. And the king of the resonant frequencies, the worst destruction possible, is what we call an F fund, right? So the fundamental frequency. That's what we're going to calculate in number 20. So if your satellite hits a fundamental frequency, it's the worst of all those resonant frequencies. It's going to shake itself to death, essentially. And it's the same thing as when you're singing in the shower. I don't know if you guys have done this, and you have shower tiles in your shower, and you hit a certain note, and it sounds like the shower tiles kind of come alive. They hum. You're hitting one of the resonant frequencies of the shower tiles, if not the fundamental frequency. So basically, when you vibrate certain objects at a particular frequency that's inherent to them, they come alive, or in a bad way, basically they start to fall apart. So by the constructive interference that occurs. So let's real quick do this math. So FatSat, yay, FatSat is a cube-shaped satellite that measures 1 meter squared per side and has a total mass of 750 kilograms. It's made out of aluminum honeycomb with a stiffness of 3.0 times 10 to the 7th newtons per meter. Calculate FatSat's F fund. I'm going to come down here to the structures equation. Let me scoot this up. We're right down here at F fund. 1 over 2 pi times square root of k, which is not the same k from the signals area. It's a different k. K is spring constant in this case. Spring constant, which is the same term as stiffness. You could see either one given to you. They mean the same thing. They're K. So K is 3 times 10 to the 7th newtons per meter. All right, let's plug and chug. This is really, really quick and easy. 2 pi times K over m equals 1 over 2 pi times square root of 3 times 10 to the 7th over 750. Let's see, 3E7 divided by 750. Too many parentheses flying around. All right, that gives us 31.831 hertz. So if I vibrate the satellite at 31.8-ish hertz, that's going to be the worst frequency for it. That's where it's going to endure the most painful resonant frequency. So you want to pick a launch vehicle wherein you don't hit that frequency. So here's what I mean by that. Question 21 addresses this, and it says FatSat is scheduled to launch on a Falcon 9. Great. Falcon 9 will vibrate all the way up to 35 hertz before it runs out of gas. So should FatSat use this rocket? Why or why not? Think about this. This is an oversimplification, but our frequency and our time here again. It says Falcon 9 is going to vibrate all the way up to 35 hertz before it, levels off because it stops vibrating. Actually, I guess I should say it goes back down. But either way, FatSat's F fund is right here at F fund right here at 31. 831. And this is 35. Basically, what I'm trying to say is throughout the course of a launch, Falcon 9 is going to vibrate all the way up to 35 hertz, which means it's going to pass right on through FatSat's fundamental frequency, and it's going to shake it to death. So if we could pick a different launch vehicle that maybe, say, only goes up to 30 hertz and doesn't hit FatSat's fundamental frequency, well, then that's what we want to do. So no, we should not use the Falcon 9. Falcon 9, let's see, actually, vibrates past 31.831 hertz. All right, y'all, I hate to call it. We did just finish the packet. Definitely open to more questions later. I have to end the recording now and jump on another meeting, but I will see you guys next time, and hit me up if there's other questions.
Thank you,
as
sir.
always, good. Yes, ma'am.
Thank you, sir.
Oh, thank you. Oh, yeah, you're welcome. Talk to you guys soon.